Welcome back. Now, today, in the last class, we were discussing about how to plot radial distribution functions, right? That is the radial part of wave function. We know that our radial wave function psi, our wave function, total wave function psi, which depends upon three quantum numbers, NL, M, and three variables, R, and the angles theta and phi, which can be conveniently written as a radial function, which is RNL of R, and angular function, which is YLM theta phi, where these angular functions are known as spherical harmonics, and radial function, which is what we were plotting in the last class together with the R square. And we have seen for many orbitals, 1s atomic orbital, 2s atomic orbitals, etc. The radial function in terms of radial distribution, radial probability densities looks in this form, right? And we have also seen there are some points where the probability densities are zero. And these are called radial nodes or spherical nodes. Sometimes they are known as spherical nodes. Spherical nodes. So we have seen that in general for ns atomic orbital, number of radial nodes are n minus 1. Say for example, 1s atomic orbital, there are no nodes, and 2s it is there is one spherical node, 3s there are two spherical nodes, etc. Now, if we plot the similar function for 2p atomic orbitals, p functions, it is 2p orbitals. Now, let me tell you how it looks like. So, what we have to plot? We have to plot the radial part of the wave function, modulus square into r square. Say if it is along only on one dimension, then this r can be replaced by x. So x square modulus of r of x square. So this is the probability density. Now versus r for 2p atomic orbital, it looks like this. So similar to 1s atomic orbital, but there is a small change that its most probable distance that is here will be higher than 1s atomic orbital. Most probable distance is higher than 1s atomic orbital. Now for 3p, if I plot 3p, there will be one node. Something like this. Goes like that. So it looks like this. And you can see that there is a node here. There is a node. So the nodes for p orbital nodes starts from 3p. So in general for np orbital, number of nodes are n minus 2, right? So for 2p there are no nodes. For 3p there is one node, etc. Now you can now guess what the function, radial function or radial probability density for d orbital. We know that d orbital starts with 3d. N is equal to 3, right? N is equal to 3. For n is equal to 3, L is equal to 2. This is actually 3d, right? So for 3d, you can find that there are no nodes, but the most probable distance is higher than 1s and 2s as well as 2p. And in general, the number of nodes are n minus 3 for 3D. Therefore, for 3D orbital, it is n is 3, so 3 minus 3, there are no nodes, 0 node. For 4D, there are 4 minus 1. It is 4 minus 1, 4 minus 3, that is 1 node, etc. So in general, the number of radial nodes or sometimes called spherical nodes is obtained by using the equation n minus L minus 1. This is for every atomic orbital. Say for example, if we apply for 3D atomic orbital, we know that n is equal to 3. For D, it is L, that is equal to 2. So n minus L minus 1 means 3 minus 2 minus 1, that is equal to 0. That means there are no radial nodes or spherical node for 3D atomic orbital, right? So this is the equation. This is the equation used for calculating number of spherical nodes or radial nodes. All right. Now, so that is the plot of R of R. We have seen our wave function psi is a function of R and a two-dimensional function of theta and phi. R of R is one-dimensional and y theta phi is a two-dimensional function. So this is our phi. This is our wave function. Now we have seen how to plot this part, R of R. Now, let me show you how to plot y theta phi. That is angular plot. Angular function. Angular wave function. So this, if we plot the angular function, which depends upon two angular variables, theta and phi, we will get the shape of the orbital. And we know that 1s atomic orbital is spherically symmetrical and hence it is independent of theta and phi. So actually the theta phi dependence comes from p orbital. S orbital is independent of theta and phi and is known as spherically symmetrical functions. Spherically symmetrical. So S orbitals are usually spherically symmetrical. Say if I give you the three-dimensional picture of S orbital, so this is how S orbital looks like. So this is the angular plot, spherically symmetrical function, 1s atomic orbital. This one is 1s atomic orbital, 2s and 3s atomic orbitals. This is how S orbital looks like. Now, if we plot the angular function of p orbital, it takes this form. So this is how we get the angular function for p orbitals. So what we are plotting? We are plotting y, lm, theta and phi. This cannot be plotted using the normal graph paper. We usually use polar graph papers. For plotting this, we usually use polar graph papers for two-dimensional thing. And for three-dimensional plotting, we need some softwares. So this is how PZ orbital looks like. This is the picture of PZ orbital. And you see that PZ orbital is something called dumbbell shaped, right? This is the PZ orbital. And you can see that there are two lobes that is oriented along z-axis. That is why it is called PZ orbital. And there is yet another orbital which is called PX orbital. PX orbit, this one. And this PX orbital, you can see that the axis is, the lobes are oriented along x-axis. Lobes are oriented along x-axis. You see that this is x-axis, this is z-axis, and this is y-axis. So it is, since the lobes are oriented along x-axis, the orbital is called PX orbital. And for the third kind of p orbital is PY orbital. So this PY orbital is, lobes are oriented along y-axis, and hence that is why it is known as PY orbital. PY orbital. So these are the three p orbitals. P orbitals. We know that for p orbital, L should be 1, right? For p orbital. So it starts from n is equal to 2, because for n is equal to 2, L can have value 0 and 1. So this 1 corresponds to p orbital. And we see that for L is equal to 1, there are 3 m values. First one is m is equal to -1, 0, and +1. -1, 0, and +1. That means there are 3 p orbitals. 3 p orbitals for each shell, for each n value. Say, for example, if n is 2, there is 2p, 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 3p orbitals. One is px, other is py, and third one is pz orbital. And these p orbitals takes this figure. And you can see that this is plotted by plotting the probabilities. See, you can see here, these are plotted by plotting the modulus of psi square d tau. And for angular part only. We are not plotting the radial part, we are plotting angular part only. Okay, now if we plot, we have seen that 2p atomic orbitals are of three kinds: 2pz, 2px, and 2py. Now, if I plot it this way, this is actually the plot for 2px and 2py and 2pz. We see that for between each lobes there is a plane. In that plane, the probability of finding the electron is 0. So for 2px, this is the plane where the probability of finding the electron is 0. And such a plane is known as nodal plane. So for 2px, there is one nodal plane, and in that nodal plane, the probability of finding the electron is 0. For py also, you can see that in between lobes, you can see here that there is a plane that is along xz axis, right? That plane is along xz axis, and in that plane, probability of finding the electron is 0, and hence we can say that there is one nodal plane. Not node, we usually say it as a nodal plane. So for 2py also, there is one nodal plane. Nodal plane. Now for pz orbital, similarly for pz orbital also, there is one nodal plane. And you can see that for all p orbital, whether it is 2p, 2p or 3p or 4p, you will have at least one nodal plane. There is one nodal plane for each p orbital. Each p orbital. So we have seen that for p orbital, there is one nodal plane. Now what about s orbital? If you come to the case of s orbital, here there are no such planes, right? Because it is spherically symmetrical, there are no planes about which the probability of finding the electron is 0. So for s orbital, there are no nodal planes. For s orbitals. Now, what about d orbitals? Then after p, we have seen that the next orbital is d orbital. For d orbital, you can see that if it is x-axis and this is y-axis and z-axis is perpendicular to this plane, that is projecting towards you, then for d orbital, there are 4 lobes like this. Four lobes. Like this. And this orbital is known as dxy orbital. dxy orbital. For dxy, you can see that the lobes are in between x and y axis. In all d orbitals, in d orbitals, the lobes are for say for example for dxy orbital, lobes will be in between axes. So similarly, if I plot dyz orbital, dyz, so assume that if I rotate it something like this, suppose this is y z axis and x is projecting towards you, that can be, see if I rotate the axis to 90 degree, you can obtain this kind of structure, right? So for that, the lobes are in between y and z axis, and this orbital is known as dyz orbital. This is known as dyz orbital. Similarly, you can see that there is one more orbital, that is the xz orbital, in which lobes are in between x and z axis. So there are 3 d orbitals of similar kind: the xz, the yz, and the xy, right? dxy. And there are 2 more d orbitals, which are the x square minus y square and dz square. And if I plot this dx square minus y square, it is a little easy. This is x and y. Assume that this is x and y. Then dx square minus y square, lobes are like this. You can see that in this case, lobes are along the axis. Here, this is one lobe that is directed along y-axis, 2 lobes directed along y-axis, and the other two lobes are directed along x-axis. Whereas in dx, see this orbital is dxy orbital, right? xy orbital. And you can see here, this is dx square minus y square orbital, in which lobes are along x and y axis, whereas in dxy orbital, lobes are in between the axis. They are not along the axis. So this is dx square minus y square orbital. And we have one more orbital, dz square orbital, in which case this is z, and this is x, and this is y. Say, for example, this is x and this is y. Then you can see that there is a disk kind of probability along xy plane, xy plane. It's a disk kind of probability, and there is a lobe along z axis. So this is the structure of dz square orbital. So there are 5 d orbitals. 5d orbital. One is dxy, second dyz, dxz, and another one is dx square minus y square, dz square. All this d stands for L is equal to 2. Azimuthal quantum number L is equal to 2, right? So the d orbital starts with L is equal to 2. So n should be at least 3. Because for n is equal to 3, L can have value 0, 1, 2. So for this 0, it is s orbital, 1 is p orbital, 2 is d orbital. Now if I plot the d orbital, if I show you the d orbital in a more graphical way, this is how d orbital looks like. It's the d orbital. Now in this case, you can see that there are 2 nodal planes. Apart from for p orbital, we have seen that there is only one nodal plane. For d orbital, you can see that there are 2 nodal planes. Say, for example, in 3dxy, in which lobes are along y and x axis. In between x and y axis. See here, this lobe is in between x and y axis. You can see that there are 2 planes. This is the plane 1. This is the plane 2. There are 2 planes in which the probability of finding the electron is 0. For 3dxy, 3dxz, 3dyz, and 3dx square minus y square. Not in the case of 3dz square. Actually, in this 3dz square, there is a cone. There are 2 cones in which the probability of finding the electron is 0. So in general, for s orbital, there are no nodal planes. For p orbital, there is one nodal plane, and for d orbital, there are 2 nodal regions or nodal planes. And in general, there is n-1 nodal planes. n-1 nodal planes, or if we write it as nodes, there are n-1 nodes. So if I write the number of nodes, number of radial nodes is n minus L minus 1. number of nodal planes, or they are known as angular nodes, right? Their nodal planes are also known as angular nodes. So the number of angular nodes, that is just we have seen it is n minus 1. So the total number of nodes is it n minus 1? No, sorry. I'm sorry. It is not n minus 1. It is actually L. Number of node is equal to L. Say for example, for S orbital, L is equal to 0. For p orbital, L is equal to 1. For d orbital, L is equal to 2. So for s orbital, there are no nodes, it is 0. For p orbital, there is one nodal plane or one angular node. And for d orbital, there are two nodal planes or two angular nodes. So the number of node is L. So nodes, I'm sorry, it's not n minus 1. Number of node is equal to L. So what is the total number of nodes? Total number of nodes is equal to n minus L minus 1 plus L. If I add both, then it is n minus 1. So these are about number of nodes. So I'm stopping it here. The next class, I will discuss the different types of quantum numbers and the different rules, or just like Aufbau principles, Hund's rules, Pauli's exclusion principles, etc.